So now you guys can mute yourself unless you're going to speak. Okay. So last time we did Sterling numbers of the second kind, and this time we will look at the first kind. And unfortunately, I mean, there are more things. I mean, I plan to do 2 or 3 lectures on this topic, but next week there is going to be a lecture on graph theory. There's going to be a seminar on graph theory. So I thought next 2 lectures I can, so that will be on Tuesday. So I thought next 2 lectures we'll do some graph theory. And then we'll see what to do. So this is just to get you the notation and stuff like that, so that next week's. So next week the seminar is really good. There's a chap called Nishad Kothari, and he did his PhD from Waterloo, University of Waterloo in Canada. And for many years, this was the center of graph theory because a person called Bill Tutt was here. And this is a very famous department. And in fact, Maple was developed here. So its computer science department and math department are very well known. Combinatorics department are very well known. And well, Bill Tutt, you can read about him if you want. There is this famous article called Squaring the Square. I might have mentioned it. It's about 4 bright young undergrads who solved a big problem. And there is a, have I told you about this person? No. Have I told you about this one? Blanche Descartes?
No, Professor.
No or yes?
Negative, no, Professor.
No.
Professor, is this Descartes from way long back?
No. So you heard of Bourbaki, right?
Yes, Professor.
So Bourbaki is a fictional group of people, and they did a lot of their works. They wrote the textbooks and so on under this name, Nicholas Bourbaki, and so on. So Blanche Descartes was four graph theorists, including Bill Tutt, and she has the worst. So Ayush, switch off your mic because I can hear myself here. So, uh, so Blanche Descartes is 4 graph theorists, fictional character, and you see references to her all over the place. She's also got some, uh, papers, some easy papers of these 4 people who star over here. So 4 bright young people in Cambridge, they solved a big problem, and they described the solution in a column in Martin Gardner. If you Google this, you'll find it. It's really interesting. And then 3 of them became preeminent graph theorists after that. And Blanche Descartes was some funny character whom they invented. And they insisted that it was a real person. Anyway, so uh, let's get on. So definition of permutation. we will also call it n permutation, is a bijection from IN. I don't know why writing has gone back. So it can be viewed as um, a list. So n1, n2, n, n, well, n is a bad idea. m1, m2, mn, where mi's belong to in and are distinct, right? So for example, I can say 3, 2, 1, 4. This represents the permutation 1 goes to 3, 2 goes to 2, 3 goes to 1, 4 goes to 4. This is a two-line representation. And has everybody here done algebra 1? Anybody who hasn't done algebra 1?
No, I haven't done algebra 1 yet.
Okay, so well, it stars very prominently in group theory and in mathematics. So it's a very important kind of object, and we can in combinatorics textbooks, this is how it's defined: a k permutation on n letters uh, is a list m1, m2 up till mk, such that mi belongs to in and mi's are distinct. So proposition, let p and k be the number of permutations, number of k permutations. On n letters. Then ENK is n into n minus 1 into n minus k plus 1, and 2 pnn is equal to n factor. So I mean, this is the first thing that one proves um, in a combinatorics class, and the proof is very easy. But I'm going to give a more involved version. Um, and the reason I'm giving you an involved version, so this we did on the first day, the fundamental theorems of counting, counting in two ways and so on, because sometimes in combinatorics it sometimes seems that the proofs are a little bit a hand waving type. So whenever you feel that your proof you're not understanding, then you go back to these principles and make your proof according to. So there is some practice which is needed for this hand wave, for this fundamental, using these fundamental theorems. Most of the time we don't use them and take them for granted, but it's a good idea to do so in the first course for sure. And for especially in, I remember when I took representation theory, I did a lot of results by using this. A lot of my homeworks were using this, so it was quite useful. So let us first prove it. Prove 1 for k equal to 2. So what I do is I take ui to be the set IA for So I is fixed, A belongs to In, and A is not equal to I. And the number of elements here, this is the number of elements in UI. This is how many? So
N minus 1.
yeah, I is fixed, so the rest count for N minus 1. So this is true for every I. Right? And each UI is a set of two permutations, and with first element I. So their UIs are pairwise disjoint. So the number of um, two permutations are union of UIs. And since they are disjoint, this is this. And each one is n minus 1. So it's this. I going from 1 to n. So it's n into n minus 1. So here so I have to actually construct some kind of set to make it rigorous. I need to sometimes just make a set so that it's clear that. Now the same thing can be argued by saying that the first part can be done in n ways and second n minus 1 ways and so on. But this is the real thing. So now we extend by induction. We extend by induction. So we take, let u of m1, m2 up till mk minus 1 be this permutation, and A, where A belongs to In and A is not equal to Mi or any I. So now how many of these are there? So there were possibly k minus 1 of them. So the only possibilities are n minus k plus 1. And the same argument or similar argument shows implies that p and k is equal to whatever the number here times this guy, which is n minus k minus 1 plus 1. So this completes the proof. And part 2 is put k equal to n in 1. Okay, any questions on this? So the reason why I've given this proof is that the fundamental theorems help in writing rigorously. So whenever you are in doubt, whatever you're doing, this is a good approach to take. So let me give you some history. There was a guy called Montmort, Pierre Raymond de Montmort, and in 1708 he wrote a textbook. He wrote a book on probability theory. And it's actually book was on gambling. gambling and games of chance and so on. So you can imagine that he was quite popular. Um, and he defined permutation as follows. So an urn has n balls labeled 1, 1 through n, 1, 1 to n, and uh, pick a ball. Um, so pick a ball and note its number. This forms a permutation. So a coincidence occurs if the kth ball drawn is labeled K. Okay, this looks like drawn, but it's actually drawn. Okay, and he asked um, for the probability of um, you know probability of drawing a derangement, which means a permutation with no coincidences. So he called it the problem de rencontre. I don't know how to pronounce it, but this means coincidence. And he didn't solve it in that. Then one of the Bernoulli solved it, and then he solved it later and gave a solution. Okay, so this is our goal right now. So a fixed point. Let Sn be the set of all permutations on n letters. So it's actually a group. We go to a darker thing, and let pi belong to Sn. So basically, what is pi? Pi is some function. So pi of 1 is something, pi of 2 is something, and so on. And a fixed point is a k such that pi of k is equal to k. That's all. So if 1 goes to 1, this is a fixed point of this permutation. Okay, and a derangement is essentially a permutation with no fixed point. So a derangement is a permutation with no fixed points. So in probability books, I've seen this, problem stated as follows. So there is uh, you write some n letters and you have n envelopes and you randomly mix them. And what is the probability? I mean, you don't notice who you are sending to or who you are addressing to. What is the probability that nobody gets the right letter, or at least one guy gets the correct letter, or so on? So they try to find the probability. So let Tn denote the number of derangements in Sn. Okay, so we want to solve this, find Dn. So the problem, Montmont's problem is solve, find Dn. By the total number of probability, we want to find probability. So find Dn over n factorial. So first of all, let's find Dn. So notice that n factorial is equal to n choose k dk. Why is this? So this is number of ways of choosing n minus k points numbers from In. So what we do is we choose n minus k numbers, and the rest of them we make sure that they have no fixed points. So this is the number of derangements on k points, and these are going to be fixed points in the permutation. So this whole story over here, this becomes number of permutations with exactly k n minus k fixed points. Is that clear? This summand. So I choose out of 5 I choose 3 of them to be fixed, right? And the other guys I make sure that it's a derangement. So in this case the other one is there is only one. These I have chosen. Now I can choose these 3 in many ways. So I can choose 1 to 4, and then I can mess around with 5 and 3, or I can choose 1 to 5 and then I do 4 goes to 3 and so on. So this will give me all the permutation with exactly 2 fixed points, and I sum over this, and this gives me all the permutation. So again, if this confuses you, you make a set UI such that whatever. Okay, is that clear? This is fine?
Yeah.
Is that okay? Now you recall your homework problem. Recall that if Bn is equal to summation n choose k, k going from 0 to n, then an is equal to summation k going from, this is what you have discovered, n choose k bk, right? So this is of that form. So we get, so let's call this star. Bn is equal to k going from 0 to n minus 1 raised per n minus k, n choose k factorial. Is this okay? This is fine? Please say something, somebody.
Yes, Professor.
Okay, so let's simplify. minus 1 raised to n minus k, n factorial over k factorial, n minus k factorial, k factorial. So we get n factorial, k going from 0 to n, minus 1 raised to n minus k cancels over n minus k factorial. And this is n factorial, and I can reverse the sum and write it like this. So dn over n factorial is equal to. So this solves Montmore's problem. And do you notice something? What's the limit as n goes to infinity of dn over n factorial?
1 by e.
So this is e raised power, the first few terms of e raised power minus 1. So the required probability goes to as n goes to infinity. Okay, now any questions so far on this guy? So we solved one problem involving permutations, and I had mentioned earlier that uh, that this is equivalent. This inverse relation is equivalent to inclusion exclusion, right? So interpret this side as having exactly, and then this guy you can interpret as at least kind of story. So at least k points are not fixed, right? So choose n minus k points, and then k factorial. So at least n minus k points are not fixed. You can interpret this. So there's an at least and exactly, um, well, whatever. So when you have to solve for this at least business to exactly, then you do inclusion exclusion. You put a minus sign there. You say at least n are there, not fixed, minus n minus 2, minus, minus n minus 1 plus n minus 2 and so on. And then you get an inclusion exclusion kind of argument. So this is an exercise. If I remember, I'll put it in the homework. But this is how it's usually done. So inclusion exclusion is essentially this guy. So union of AIs is equal to the cardinality sum of AIs minus AI intersection AJ plus AI intersection. Hang on, let me go to the other line. So I not equal to J and so on. This is inclusion exclusion, and that is completely um, equivalent to whatever we did. Okay, any questions so far?
Professor,
Yes, Preetham.
so I was thinking like the way we are saying this is as picking out derangements from a box of balls, and it seems like if I add a ball to the set, then the probability would decrease and then again increase and then again decrease, and I mean that seems like a very strange phenomenon. That
I mean, the sequence can go like this.
Yeah, yeah. No, no, Professor, like I understand the math of it and all, but yeah, I'm thinking like how to explain that if I have 5 balls instead of 4 balls, then the derangement is more probable, and then I have 6, then it's again less probable.
Yeah,
And
yeah,
yeah,
yeah. So it's okay. I mean, these are alternating series. This is the sign of. Um, so even lot of sequences are like this. They go up and down and they meet. An alternating series. I mean, they're well. This one is not. This is absolutely convergent. But yeah, I mean, it's an interesting thought that you've got. That when you add one, then it will either increase or decrease, and then you add another one, it will go the opposite way. Yeah, so Montmort was very excited about this problem, and he couldn't solve it initially. And then Bernoulli's gave a solution. So I mean, these are hot problems in 17 or something, 1700s, and one can see why. I mean, this is very exciting. But this is quite remarkable. It's a somehow. It's a non-trivial theorem, even though it comes out very easily for us. Okay, by the way, my first paper was in this topic, Stirling numbers and all. I've forgotten what it was, but still, on inverse relations. Um, and here's a coincidence. Um, um, so when I finished my PhD, this was in 1995. The internet was just starting, So Netscape had just come. Netscape was a browser. It was written by a chap called Mark Andreessen. So Mark Andreessen wrote a graphical browser. Suddenly the internet took off because people were able to see. Then he formed a company called Netscape, which made no money, but it was really famous. And then everybody bought the code from Netscape and included into Windows and this and that. So internet was all text based until that time and very limited. So this was when I did my PhD, and then my daughter was born the same year. And my paper had come out, the first paper, and it was the first sentence was consider the problem they rencontre exactly as I told. This was the first sentence of my first paper, right? And this means coincidence. Okay, so then my daughter was born, and this friend of mine said, there is this website, you can go and check if there are any mathematicians who were born on the same day. Okay, so I went and put in my daughter's date of birth, and guess what I found? Pierre Raymond de Montmort. This paper was written 2 years before, but apparently his birthday was the same as my daughter's birthday. So that was a big coincidence, I would say. Do you agree?
Yeah. Professor,
yes, sir.
what was the paper about?
Paper was about inverse relations. I mean, the basic idea was my advisors, and then I extended it that if there is a certain, so we saw this, right? We saw this fnk is equal to fn minus 1k plus uh, fn minus 1k minus 1. So this was one, this was a recurrence relation satisfied by one guy, and this was the inverse relation satisfied by another guy, I mean, with some slight changes here. And same issues with Stirling numbers, where there was a k here and there was an n here, right? So my advisors basically had a theorem which said that if you know a recurrence of this type, then you can predict the recurrence of this type. So if you had an fk here, then there'll be a fn here or something like that. Some such recurrence. And then that was what the paper was. So this worked in Stirling numbers and every inverse relation. So we had a characterization. So anyway, Okay, so here's a proposition. So people who have done algebra pretty much have got, they have, you know, seen these kind of things before. Every permutation um, can be written as a product of cycles, of disjoint cycles. So what are cycles? A K cycle um, is a cyclic arrangement or an arrangement in a circle. So we are looking at A1, A2 up till AK, and with the so let me say we denote it by with the understanding that A1, A2, AK is the same as A2, A3, AK, A1, and so on. Keep circling through that, and so you can at some point begin with AK, A1, A2, and so on. So it's easy to see that there are exactly k minus 1 factorial different cyclic arrangements. So I mean, you put all arrangements and you divide by k of these. That's what you get, this k minus 1. So essentially, this is the issue. You put these together, A5, and then you can rotate them. If you rotate, it's the same thing. That's it. So let's look at the proof of the proposition. So let pi be a permutation. On n letters. So pi belongs to Sn. So consider 1, pi 1, pi of pi 1, pi of pi square 1, and so on. So it's a finite set. So for some k, pi raised per k of 1 is going to be 1. And choose the smallest such k. Well, let me do k plus 1. So this is a cycle. Well, k is good, not k plus 1. This is k minus 1 is a k cycle in pi. Now pick next guy, pick something not in here and do whatever. Let's say a, then do pi of a and so on. So keep going until you cover all the letters. I'll just do an example very quickly. So let's see. Well, I have a trivial example. So example. So let's say this is 4, this is 5, this is 2, this is 3, this is 7, this is 6, and what's left? 1. So start with 1, 1 goes to 4, 4 goes to 3, 3 goes to 2, 2 goes to 5, 5 goes to 7. Well, this is a really trivial example, but this is it. So you start with 1 and you get a cycle, and then and this is all these conditions will be met, that it is a disjoint cycle and so on. Okay, so this brings us to Stirling number. So I'm going to define, let C and K. Well, eventually I'll make it S and K be the number of permutations with exactly K cycles. Okay, and then C and K is nothing but our S and K, the Stirling, what we defined in your homework of the first unit. Actually, I should add that we also say over here, somewhere you will also find this kind of terminology, that S and K is the number of ways of uh, decomposing an N set into K cycle, K disjoint cycle. So I mean, this particular object is very important in mathematics, the permutations, and um, so it appears in many contexts. So purely combinatorial text will be writing it like this. An algebraic test will be looking at permutations in general. And let me say this again, a class of permutations. These are called conjugacy classes actually. Is a set of partitions um, of a particular cycle type, and that is determined by a partition. So partition meaning, so for example, if phi is 3 plus 2, this is a cycle type. So a 3 cycle plus a 2 cycle. So permutations of S5 can be split into these, and these are, so this is a partition of 5. Similarly, there's another partition, 2 plus 2 plus 1. So this will give you another partition. So there are two cycles and one cycle. So example here is let's say 1 3 2. That's a 3 cycle, and a 2 cycle, which is 4 5. And an example here is 1 2 3 4 and 5. And what is really fantastic about this guy is that it's an equivalence relation. So there is a very important equivalence relation which we may or may not get into. But this is these classes are very natural. So there is a there is an equivalence relation which leads to these classes. Yeah, so I don't know, I mean, if we get a chance to do this kind of a little bit of algebra, but this part of algebra is also related to counting. So earlier books, used to talk about counting principles and so on, and this is what it was. And one thing to note is, so let's get some familiarity now. One thing to note is for any, so this is what I do for every guy actually. For any set, whenever I see a thing, so I want to, show it to you also. For any set partition, it corresponds to one or more cycle decompositions. So let's do some example. So let's take n equal to 4 and k equal to 2. So what are the, so this leads to certain, so you can have 1, 2, 3, 4, and we can have 1, 3, 2, 4. These two are different, they're not cyclic arrangements. And similarly, you have 2, 3, 1, union 4, oh, this is the same thing, 2, 3, 4, union 1, and this will lead to 2, 3, 4, 1, and 2, 4, 3, 1, right? Then 1, 3, 4, union 2, 1, 2, 4, union 3. So these are all set partitions and they'll all correspond to two of these. So 1, 3, 4, 2, and 1, 4, 3. And this will correspond to 1, 2, 4, 3, and 1, 4, 2, 3. So these are all the ones with 3 and 1. So these are corresponding to 3 plus 1 partition. And then there is a 2 plus 2 partition. So we have 1, 2, union 3, 4, 1, 3, union 2, 4, 1, 4, and 2, 3. Right? These don't correspond to anything extra. But these correspond to multiple ones. So whenever you have more than transpositions, that's when you get more and more complicated. So I think one thing is clear. What is clear? Small SNK is going to be bigger than capital. Yeah. Yeah, Ayush?
I was just saying this the same thing.
Okay, okay. So I took the words from your mouth. So this is clear and the proof is also clear. I mean, I'll just note it. For every set partition, there is at least one cycle partition. So again, in computer science, these numbers come up all the time. So if you look at, if you look at concrete math, which is this math, you'll see a lot of the stuff that we are doing is all covered there. Okay, so let's enumerate. So again, I like to do this with every object that we study, that I study. I first try to enumerate and understand what they're really saying. And that's the way to understand combinatorics or to do proofs or whatever, is to mess with the numbers. And you have to be willing somewhat to get your hands dirty. Okay, so let's do the usual stuff. Let's list all of them. So S00 we take to be equal to 1. So this is just an empty cycle. Now for n equal to 1, breaking into a 0 cycle is not possible. So for one cycle, one part is this one. So K is the parts, and this is the IM. Right. Let's do 2. Again, for 0, there is nothing. So why written B? Okay, so two elements in one cycle. Here there is only one possibility, and into two parts, this is the only possibility. Let's try 3. Into one part, now we have multiple possibilities. Into two parts, 1, 2, and 3. 1, 3, and 2, and 2, 3, and 1. So far it looks very much like whatever we had. Okay. 3, there is going to be only 1. So again, one thing is coming out clearly. Oops. That SNN is also 1. And of course, SNK, okay, bigger than n is going to be 0. These are 0 over here. Okay, let's go more. Let's do 4. Nothing here. Now, here. Now, here, it's an interesting thing that one can think of putting a 4 anywhere here. So 1, 2, 3, and I can put a 4 here. So I sometimes don't write the commas. And then I can have 1, 2, 4, 3. Maybe I need a bigger. So somewhere we are seeing some kind of pattern here. And I can have 1, 3, 2, 4. Oh, one more here. 1, 4, 2, 3. And I can do 4, 1, 2, 3. So I can just place a 4 anywhere over here. And then I can also do the same over here. 1, 3, 2, 4. 1, 3, 4, 2. 1, 4, 3, 2. 4, 1, 3, 2. Okay. Okay. Now this guy. So 4 into 2 parts. So one thing I can do now you're beginning to see the pattern very clearly. Okay, I can add, I want 2 parts. So this guy has 1 part, the one on the left. I can just add 4 as a part. Here, I can add a 4 anywhere. Before 3, before 2, or before 1. So I can have 1, 2, you know, 4, 3 or 3, 4 is the same thing. Well, we can do after 1. Before, okay. 1, 2, 4, 3. or I can do 1, 4, 2, 3, or I can do 4, 1. I mean, before or after doesn't matter because I'll cover all of them. Let's do this guy. This guy. So I can put it. Let me put it 1, 3, 2, 4 this time after 1, 3, 4, 2, and 1, 4, 3, 2. So if I put a 4 here, it's the same as 1, 3, 4. Right? So I can choose to put before or after whichever guy. And then the last guy for this guy, I have 2, 3, 1, 4, 2, 4, 3, 1, and 4, 2, 3, 1. Okay, so that covers all of them. So all the ones, if I delete the 4s here, I'll get one of these guys, and I can delete from anywhere. And vice versa, I can insert a 4. Is this clear? Is the process clear? So let's just do this guy again. I can put 4 as it is over here. So I need 3 parts. Over here, K is 3. So I need 3 parts. So here there are 2 parts are already there. So I can put a 4 on its own. So 1, 3, 2, 4, and 2, 3, 1, 4. And here I can put a 4 anywhere I want. So 1, 2, and so after any one of the other guys, 2, 4, 3, and 1, 4, 2, 3, and I've got. So these are all the guys. And then there is one chap with k equal to 4, which is just this guy. So we can insert the, you know, basically so what I'm going to do is right now, so earlier proposition, I had C and K, but since it's going to become S and K, I'll just write it in terms of S and K. So let S and K be the what C and K was. We will show this proposition. So S and K is equal to S n minus 1 K minus 1 plus n minus 1 S n minus 1 K minus 1. S00 equal to 1, Sn0 equal to 0 for n bigger than 0, and Snk equal to 0 for k bigger than n. And then as a remark, we'll say that this is the same as what you defined earlier in your input. Okay, is this clear? I mean, more or less the idea is clear to everybody already, so I'll just write down the proof. Is this clear? I mean, you probably can write it down yourself, but we'll just say that initial and boundary conditions, that's okay. So these parts are okay. And for every cycle decomposition of in minus 1 into k cycles, we get n minus 1 decompositions of In by inserting N before or after. I mean, one of the things we have to do. 1, 2, 3 till N minus 2. Okay. And in addition, we can place a cycle N after every K minus 1 cycle of I. So the process is reversible. Get Sn k is equal to Sn minus 1 k minus 1 plus n minus 1 Sn minus 1. Remark, since Sn k as defined here satisfies the same set of recurrence plus boundary conditions, initial plus boundary, as and these conditions determine Snk. So you can see, I mean, we can make a table. We'll make a table. The two definitions are identical. So two definition meaning the other definition was in your assignment 1. Okay, so using this we can make a table. So of course you made it using the computer, but again I always try to do it by hand just to get a feeling. N and K, so 0 is of course 1, 1 is 0 and 1, 2 is 0, and we are taking n minus 1 times this plus this guy, so it's 1. N minus 1 times and 2 is always equal to 1, so this is okay. 3, this is n minus 1 times this plus this, so that's 2. N minus 1 times this plus this is 3, so n is 3, n minus 1 is 2, so 2, 3, and then 1, 4, what do we get? 6, 9 plus 2, 11, 3 plus 3, 6, and 1, 5, this is 24, this is 51, no, 50, and this is 24 plus this 35, then this is 4 plus this 10, then 1, and so on. I'll just write down. Okay, so from the table it is apparent, it should be apparent, since we are able to make the table. It's a practical way of knowing that recurrences determine the numbers. I mean, this is an obvious thing, but um, you know, one has to understand very clearly that when you make recurrences, then do they actually determine the numbers? Otherwise, it's no point. Okay, any questions so far? Any questions? Are you guys still awake or taking a nice nap? Any queries?
No, Professor.
Okay, so the next topic and the last one for today is inversions. I think we have more than enough time. So this is an idea of what is an idea, a big thing of a field of called permutation statistics. So you haven't seen any examples of this, but we take a combinatorial object, and actually we have seen some examples. But anyway, we take um, an object like permutations over here, and then try to find some statistic, and then check what it's what it tells. Is there anything which can be said about this? And the statistic that we are going to use is called, so pi is a permutation in Sn, so n letters, and let I of pi be the number of inversions in pi. So what is an inversion? If I is less than j, but pi of I is bigger than pi of j, then it's called an inversion. So let me do some examples. So in n equal to 2, these are the two, n equal to 2, these are the two permutations. So what is the inversion here? There is no inversion here. And here there is one inversion. So 2 is, so what we do, I is less than j, that means you look to the right and see if something is bigger than 2 and is smaller than 2. So pi of I, the pi of 1 is bigger than pi of 2. So here the number of inversion is 1 and here it's 0. So what we are interested in is looking at this guy, the generating function, and in this case the generating function is 1 plus 2. So this doesn't make, let's try 3. So there's 1, 2, 3, 2, 1, 3, 3, 2, 1, 1, 3, 2, 3, 1, and 3, 1. I think I've listed all 1, 2, 3, then 2, 1, 3, then 3, 2, 1, then 1, 3, 2, 2, 3, 1, 3, 1. Yeah. Okay, so so these are the pi. What are the inversions? What is the inversion number? So there's nothing here. Here there's one inversion for 2 and nothing here. So you go look left to right, see how many numbers are big. So smaller than 3. So how many numbers are smaller than 3? 2. How many numbers smaller than 2? 1. So the answer is 3. Here 0 plus 1. Here 1 plus 1. this number is 1 is smaller than 2 and 3 is so for 3 1 is smaller than 3, that's 2, and here for 3 there are two numbers which are smaller, this is fine. So this is, so what is this generating function? This contributes 1, this contributes cube, this contributes cubed, cube, q square, q square. So if you sum all these, you get 1 plus 2q plus 2q square plus qq, and this is equal to, so is this clear? What are inversions? So you go left to right, okay, and count number of elements that are small. Let me do one more example before I write down. So let's do this. So this is an inversion, right? 1 is less than 4. So suppose I flip it. Now this is also an inversion, so I flip that. Now 2 4 is also an inversion. This is also an inversion, so I flip that. Right? Now I start here. This is fine. This is an inversion, and I flip that. So the inversions keep track of the number of flips in sorting it. Number of, I'll call them transpositions to sort the permutation. Do you get that? Is this clear? So here 4 has to be flipped with 3 of them. It does do that. Then 3 has to be flipped with 1 of them, and you do that. And the total number of inversions is the number of times to track. So I mean, you can see why they come up in computer science. Okay, so anyway, here's my proposition. Let INQ be the phi belonging to Sn, Q is for inversion of pi. Then this is equal to a Q analog of n factorial. So what is this? This is 1 plus q, 1 plus q plus q square, so on up to 1 plus q plus so on until q raised to n minus 1. So you can see this is a n factorial q when q equal to 1 will give you n factorial. Right? So it's a q analog of n factorial, and here inversion of pi is just what I've written. I of pi is number of inversions in pi, and we keep track of it, and we get this number. So poof, again you take the element n, right, and it can be inserted into a permutation of n minus 1 in uh, to lead to 0, 1, 2, n minus 1 inversions, new inversions. So what am I saying? Let me do an example. Suppose 213 is given. I want to insert 4. Insert 4. So if I insert here, this gives me 0 new inversion. If I insert here, this gives me 1 new inversion. If I insert here, then it gives me 2 new inversions. And if I insert here, it will give me 3 new inversions. So, I mean, from this example, this was our notation, right? In q is equal to, so this will lead to what? I mean, this will lead to 1 plus q square up till q raised power n minus 1. So each one will be one more to all which existed before. And we know that I2 of q is equal to 1 plus q that we calculated. This means that I in q is 1 plus q square, sorry, 1 plus q square to the 1 plus q square, so on until q is 1. That's the q. Okay, any questions? So just a remark, statistics such as with same distribution as I and B are called Mahonian. So this is after, how do I remember, major, like yeah, who discovered several. So what am I saying? I'm saying that there are, so inversion is a statistic and there are more. And if you take, so there are more, q raised power some more statistics. This guy turns out to be the same thing as the inverse, which is n factorial q. And this is quite remarkable that there is a different statistic with the same distribution. And Major McMahon discovered them first, so they're named after him. So, by the way, have you heard this name before? Have you heard the name McMahon? Have you seen a movie called Ramanujan, The Man Who Knew Infinity?
Yes, Professor.
So anybody other than Ayush, you've seen it? So this is about Ramanujan, and McMahon was a starring person there. So he was an officer in the British Army. In fact, he was posted in India. Then he went back, and after retirement, he was basically a mathematician, and he wrote a book called Combinatorics Analysis, Volume 1 and 2 books actually. Volume 1 and Volume 2. And he was a natural computer, and apparently he was better than Ramanujan. So, a lot of big deal is being made of Shakuntala Devi. Apparently, there's a movie about her, and people are claiming that she's a mathematician. But that's not true. She used to be good at arithmetic of a certain kind. And McMahon is another example of very natural computer. The point is, what do you do with those gifts? I mean, I can't calculate without a calculator or a computer, but I do mathematics. And a lot of people who can compute or calculate, they don't discover anything, they don't do any mathematics, they don't know anything, they don't know any mathematics. So this has become like they're a little bit savants kind of thing. So McMahon was also one of the guys who was very good at that, and he and Ramanujan were involved very strongly in partition. So we'll talk about that. McMahon basically um, calculated, made a table of partitions, and Hardy and Ramanujan had a formula for partitions, and they they checked that. So we'll talk about these things later on a little bit. Okay. So any queries, questions?